And now the sampling error. So in a routine practice, when we have larger populations, we usually get a statistic from sample. That is, we collect a sample from the population and we calculate the statistic from there. For example, we calculate mean value. And that statistic gives us an estimate of the population value. So usually the larger samples, they provide a more reliable estimate than the smaller ones. And if we have taken several small samples from the same population, and they generally provide different values of the same statistic. For example, if we are taking the mean value, the mean shoot length, and if we have taken, instead of taking a large sample, if we have taken several smaller samples from the same population, then each one of them is going to give us a different value of the mean shoot length. And why is that so? That difference is because of the sampling error. So is this sampling error, it is the fault in our experiment, it is fault in our sampling? No, it's not the mistake of observer, it happens by chance. And why it happens by chance is because some individuals, they have more than a fair chance of being sampled as compared to the others. So some individuals in the population, they have less than a fair chance of being sampled, and some have higher than a fair chance of being sampled. So that is why we have a sampling error in every sample. So that is the inherent property of every sample, and that is not at all the mistake on the part of the observer. So what do we do to correct that sampling error? We calculate standard error, and the formula for calculation of standard error is standard deviation divided by the square root of number of observations. So again, recalling the example of shoot length, where we calculated the standard deviation to be 2.34 millimeters and the number of observations were 100. So standard error is 0.234 millimeters. So mean shoot length of the sample is 74 millimeters and the standard error of the mean is plus minus 0.234 millimeters. So we can use a standard error in the calculation of confidence interval. So what is confidence interval? It is the estimated interval of population mean. So it is an interval, or it is a range of values, a range of observations in which our population value is expected to lie. For example, if we have calculated the population mean, then we calculate the confidence interval of mean. So confidence interval of mean gives us two values, and it gives us an interval or a range in which our population mean is expected to lie. And this is calculated by taking the sample mean plus minus z-score standard error. So in a normal curve, in a larger sample, which usually give a smooth normal curve, so in a normal curve, the standard error plus minus 1, so plus minus 1 standard error, so that gives us a confidence level of 68%. And if we want to increase the confidence level, because 68% is not a very reliable estimate, so if we want to increase it, and if we want to keep it at least at 95% confidence interval, so in that case we have to take standard error plus minus 1.96. And if we want to further increase the confidence level, then we have to take it 2.58 plus minus standard error, and that gives us 99% confidence interval. So in case of standard error alone, we are 68% confident that population mean lies within plus minus 1 standard error of a sample mean. So in case of 1.96 z-score, we are 95% confident that the population mean lies within plus minus 1.96 standard error of a sample mean. And in case of 2.58 z-score, we are 99% confident that population mean lies within plus minus 2.58 standard error of a sample mean. But if we have the sample size which is smaller, so if by any chance we happen to get a smaller sample size, so in that case our sample curve is not going to be a smooth curve, it is not going to be a normal curve, so we cannot use the value of z. So in that case we have to use a correction value, which is the t value. So we are going to use the t value instead of z-score, and the value of value of t is taken from the t distribution table using degree of freedom and desired level of confidence. For example, masses of mammals, so this is a smaller sample. How many observations are there? There are 10 observations. So the mean mass of mammals is 21.42 grams 95% confidence interval is 20.1, 22.7 grams. So we did this calculation in the class, if you remember, and we calculated this confidence interval, and we calculated that using the t-value, and this is the table for getting the t-value, the table t-value. So using the degree of freedom for the two-tailed test and the desired level of confidence, which is 0.05, which gives us the 95% confidence interval. So the degree of freedom was 9 because the total number of observations were 10. So at 9, the table value is 2.262 at 95% confidence interval. For 0.01, it is 3.25, which is 99%.